Hi, today we are going to look at some techniques that we can use for problems involving impact. When we're studying dynamics, there's often cases that come up where you have two bodies that may have a relative velocity one to another, and they approach each other, and then when they strike each other, there is sort of kind of two phases. When they strike each other, there is the phase where they are kind of compressing the material that's in them, and then at some point they rebound, or it's kind of called the restitution phase. And so when that happens, that can happen a number of different ways, and we're going to look at some techniques that we can use to figure out the velocities that result after an impact event has occurred. So one of the key parameters that we use when we're dealing with this kind of situation is called the coefficient of restitution, and we're going to abbreviate that sometimes as COR. So coefficient of restitution. Let's talk a little bit about what that is. So again, what I've kind of set up here is, imagine that these two bodies were approaching each other, and at some point they actually began to contact one another. The only way that they would approach each other is if, before they began this process of kind of deforming and then going through this restitution phase, the only way that that would really happen is if this value over here, this velocity value, is bigger than this one, right? In other words, if VB1 was bigger than VA1, then they wouldn't actually approach each other to be able to run into one another. All right. Well, the other thing that we can say is, after they finish with this interaction that happens right here, generally what happens is VB2, for instance here, this one is now going to be bigger. Okay. And we've seen this type of thing, let's say when you see like billiard balls run into one another. When one runs into the other one, it starts out that the first one has a velocity relative to the second one, and once the impact happens, then the second one now has a bigger velocity. So this is kind of how that goes. Let's go ahead and define what this coefficient of restitution is. Okay, the letter that the textbook that we use here, the letter that they use for that is E. I'll just say I don't particularly love that, because I like to reserve E as the base of the natural log. But we'll just go ahead and again go with what they've got. What this is, it is the relative velocity of departure over the relative velocity of approach. Okay, that's conceptually what we're talking about. So basically, they have a relative velocity to one another whenever they impact, and then they have a relative velocity as they depart. Okay, and if we're going to actually state this in terms of the variables that I put on here, to have a positive difference here, in order to do this relative velocity, that's basically a difference in the velocities, right? You take the bigger one minus the smaller one, right? And that's actually, we need to look at the departure first. So during the restitution phase, that's what we're going to put in the numerator. So actually there, VB2 is bigger than VA2, and so you put that one first in the difference. So you say VB2 minus VA2, okay, where the 2 just represents kind of the second half of this collision and rebound type of a system. And then in the relative velocity of approach, you take, again, the bigger minus the smaller. Okay, VA1 minus VB1. Okay, and that's basically it. So a couple of things that we'll say about this. Okay, the first thing I want to say is that this value of E, it ranges from 0 to 1. Here's why it ranges from 0 to 1, okay? If it's 0, then that means you have 0 relative velocity of departure, okay? What is that? That is if these two things hit each other and stick, and then they have the same velocity as each other as they continue on, all right? That is called a totally plastic or fully plastic collision or impact. Sticking together kind of is about as much energy as can be wasted whenever two things impact like this. All right. If it's 1, that's on the opposite end of the spectrum, and it means that there's basically no energy lost whenever these two things hit and rebound. There's no energy lost in that impact. So you actually, with real collisions like this, you really can't actually get to fully 1. That's a perfectly elastic collision. There are no material pairs that actually give a completely, all the way to 1. Now there are some materials that do give high numbers, in 0.9 and higher, but you can't ever get to 1 because there will always be some energy lost in one of these impact kind of things. All right, so that's kind of my first note about the coefficient of restitution, as it ranges from 0 to 1. 1 means no energy is lost. 0 means kind of maximum energy gets lost in that process. And then I introduced the terms of plastic and elastic. Okay, and the further you go toward 1, the more toward the elastic end of that range you go. All right, so let me make some other notes here about these impact principles. These are just kind of a list of things that I wanted to touch on. So first of all, generally coefficient of restitution isn't enough to really handle an impact problem. What you usually do is you have to use coefficient of restitution along with a conservation of momentum principle that we've already seen in a previous class in order to figure out kind of relative velocities of these two bodies that might collide with one another after that collision, for instance, if you knew the velocities beforehand. One thing I kind of remembered here that I don't know that I put on here, in general, I'll kind of squeeze it in here, your coefficient of restitution is kind of based on material pairs. And the reason I'm hedging on that a little bit is it's not a completely deterministic thing. You can't just say I have this kind of material and this kind of material. That means I have blank coefficient of restitution. It depends on relative velocities. It depends on various other conditions. We'll just say that we sometimes treat it as if this E is a constant based on material pairs. It is a strong function of material pairs, but it's not necessarily completely determined by the material pair, the things that are going to be running into one another. All right. One thing I will say, and this is not something that means that there aren't problems that don't arise where they are maybe different than this, but in this course we are only going to think about problems where we have frictionless contact between bodies. Okay, it's not that other kinds of problems can't be handled, it's just that it makes them significantly more complicated if you're looking at sort of general impact, one body to another. If you have friction at that point of contact, it can really complicate these problems significantly. And so we're just going to limit, for the purpose of this course, to cases where we're going to say, frictionless contact between two bodies. Basically what that means is there will be no force transfer in a tangential direction at the point where two bodies meet each other. Okay? The next thing we have here is that when impact occurs with a fixed axis rotation body, rather than using linear momentum in those kinds of cases, usually what we need to use is a conservation of angular momentum in those cases, and we're going to cover an example problem here in just a moment. that allows us to handle a case like that. Okay, and then the last little issue that I want to do here, I'm going to draw a little picture so that we get the idea of what to do with something that's called an oblique impact. So let's say you have two bodies, and these two bodies wind up running into each other. Okay, so they kind of run into each other, maybe in a position like this. Well, let's say that one of these bodies had an initial velocity that was kind of coming in like this, and another one had an initial velocity that maybe was coming in like this. Okay, this is an oblique impact because they kind of have two different velocities whenever they get ready to run into each other. Okay, when we have a situation like this, the way that that should be handled is to, first of all, define this sort of line of impact, and this is sort of the plane of impact between these two things. So you set up a coordinate system like this, and I oftentimes label this as a normal direction, for instance, and maybe a tangential direction like this. All right, the way you handle this, particularly in cases where we have this frictionless contact, what we do is we say we're going to split these velocities into components, such that maybe we'll have a component going this way and a component going this way for that velocity there. Here we would have a component going this way and another component going this way. We basically split those velocities into components that are aligned with a normal and tangential type of a system. Okay? And what you do then is you take the component that is tangential, you say that tangential component for each body isn't changed. It'll just maintain whatever it started out as after the impact. And then you look at the normal component, you say the coefficient of restitution idea that we just came up with is going to apply to that normal direction. Okay, so you just apply that coefficient of restitution to the normal direction, and everything else, the tangential components of velocity remain unchanged as these bodies move through space like this. Okay, again, this applies as long as we have this frictionless case that we said we're going to limit ourselves to for now in this course. It does get a little bit more complicated if you allow friction, because now the bodies could actually start to spin, and you can end up having force transfer in that tangential direction at that point, and so that would imply an impulse, one relative to another, along that tangential direction. So maybe for those of you who get into a more advanced dynamics course, you may end up dealing with situations where you also deal with friction, but we are going to limit our discussion to ones where that doesn't occur. All right, well, let's work on an example problem so that we can actually apply some of these principles that we just looked at. Okay, here's the example that I want to look through. All right, so talk through it just for a moment. First of all, I want to say this is an example problem where we are viewing it from above. We're looking down onto this system. This plate is constrained by a pin, okay, and kind of rotating in a horizontal plane around that pin, or it's not rotating yet. It starts at rest. Before anything happens here, basically, what goes before here is that disk 1 is sliding in from the left at a speed of 30 meters per second. And it's going to impact disk 2, which is sliding downward such that it's sliding parallel with this edge of the plate with a small little gap in between. The reason that I make a big deal about that little small gap right there is that I want to make sure that we think of this as two distinct impacts. There's going to be a first impact that happens when disk 1 runs into disk 2. Then there's going to be a second impact due to how disk 2 is perturbed in that first impact, disk 2 is then going to impact the plate. And we're going to deal with those two impacts sort of sequentially here. Okay. We're given some information. Disk 1, we know its mass is 4 kilograms. Disk 2 is 7 kilograms. And the plate has a mass of 11 kilograms. And we've done some experiments with these materials, and we estimate that the coefficient of restitution for all of these collisions that happen here are going to be 0.65 for that coefficient of restitution in every case. What we need to do is find the velocities of disks 1 and 2 immediately after that first impact occurs. Okay. After that, we're going to go on and find what the angular velocity is of the plate after the second impact. So that basically happens right away after the first impact. The disk 2 then is going to run into the plate and give it some angular velocity. And then we're also going to figure out the final velocity of disk 2 after that second impact. Okay? All right, so here's what we need to do first. It really helps, in my opinion, it really helps for us to think of a diagram that allows us to talk about the different components of velocity in these cases. And so I'm going to do that for disks 1 and 2. Okay, so here is disk 1. Okay, and I'm just going to maybe label that right down here as disk 1. And here is disk 2. All right, and one of the fortunate things is that we are given what this line of impact is. Okay, so I'm going to put that in there like that and actually label it with an N, meaning that's kind of our normal direction. Okay, and then let me actually do this for each of these bodies. I'm going to show another axis that is the tangential axis. Just like that. All right, so that kind of sets up our space in which this collision occurs. Okay, we know that disk 1 has 30 meters per second velocity at this point where it hits, but that velocity is in the direction that's given there, 15 degrees basically, down from that kind of negative x direction that we have there. So let me show that on here. Okay, this is 30 meters per second. Okay, and let me show that actually relative to this x direction here. Set up my x and y directions. Okay, so that x extends back here like so. And I'll also say that this is our 40-degree angle right here. Okay, that means that the total angle on the other side of these two lines is also 40 degrees. And what that means is that this is actually 40 degrees minus 15 degrees. That's what this angle is right in here. Okay, because this is 15 degrees over here. All right, hopefully that makes sense. Okay, and it's important for us to establish this geometry because we're going to be doing some splitting of these vectors into components, and that helps for us to establish these. All right, the next one that we have is this 20 meters per second. And that's going to be going in straight in the vertical direction, right? So I could actually show here, you know, this is kind of my y direction. And this is my x direction. Okay, so I've got 20 meters per second sliding down like this. And I don't have to split that particularly into x and y components because it's entirely in the y. All right, let me put another couple of pieces of information on here. Disc 1 is 4 kilograms. Just put that there. Disc 2 is 7 kilograms. Just to have them on there. All right, so now what? Well, in order for us to deal with our equations like the coefficient of restitution, one of the things that we need to do is split these initial velocities into components that align with our normal and tangential directions. Let me do that here, and I'll first just kind of indicate what that would look like geometrically, right? You remember, you can sort of express this as a component that goes there and a component that goes here, right? And you know, when we look at those, this one here is just going to be equal to what? Well, we need to probably establish our angles. All right, if this is 40-degree angle, then that means this is a 40-degree angle. This is a 40-degree angle right here, which means this is a 40-degree angle up here. Okay. So, when we look at, you know, and I think maybe I mislabeled these. This is disc. Got a couple things mislabeled there. Disc 1 was down here. Disc 2 is right here. So that means I believe my mass labeling is also incorrect. Let me fix that. Okay, 1 was 4 kilograms. And 2 is 7 kilograms. Sorry about that. All right. So here's what we need to do. Let's figure out our component of disc 2. Okay, in the normal direction. All right. And I'm going to do this according to the positive direction I've assigned here for my normal direction. Okay. So what that means is I've got 20 meters per second times, all right, I need the sine in order to get that normal component. I need the sine of 40 degrees. Okay. The other thing that I'll do here is, in order to get that, you know, positive negative correct, notice that that component is actually pointed in the negative normal. It's the opposite direction of the direction I assigned as positive. So I'll call that a negative value there. Okay. And let me go ahead and punch that in. So I've got minus 20 times the sine, 40 degrees. And I believe I had my calculator in radian mode, so I'm going to put that in degree mode. All right, negative 12.856. Okay, this would be in meters per second. Okay, well, what about the velocity of 1 in the normal direction? Okay, that is just going to be equal to, okay, we've got to split this 30 meter per second into one that goes along the normal. So again, that's actually going to be positive, right? If I sketch this out, basically I'm saying I need the piece that goes this way, and I've got another piece that goes this way. Okay, so for that normal component, what I've got is 30 meter per second positive times the cosine of 40 degrees minus 15 degrees. Okay. And so if I punch that in, 30 times the cosine of 40 minus 15 gives me 27.189 meters per second. All right. So far, so good there. All right. So now, you know, we actually might also care about tangential directions, and I'll show you why here in just a second, but let's go ahead and figure those out as well. So V2t, this again is before the impact happens. For that, we're going to have, you know, that's going to be in the positive direction according to that t, times the cosine of 40 degrees. Okay. Which gives me 15.321 meters per second. All right. And then V1t is going to be equal to, okay, I need that piece that's up here, all right, which I can just use, instead of the cosine function, I use the sine function. So 30 meter per second cosine not cosine, sine. Of 40 degrees minus 15 degrees. All right, and so now I punch that in and I get .679 meter per second. Okay, so those are all really handy things to have, because what we're going to do next is a little system of equations where we take into account two different things. First of all, we get to use our coefficient of restitution idea that we just established, and we get to use our conservation of momentum concept that we've already talked about, but we'll show it here in a different way that we may not have seen yet. Okay. So here's what that looks like. All right. First of all, coefficient of restitution, which is given up here as being 0.65. That coefficient of restitution is equal to, okay, we need to probably think about the idea that this first disk has a higher velocity along that normal direction, right? Initially, okay, so if we're trying to figure out that rate of approach, what we're going to do is we're going to take that value, V1n, which is 27.189 meter per second along that normal direction. Okay, and then we're going to subtract the velocity that we have for the other one along that same direction. And this is where we got to be careful. We subtract to get the difference, but then the actual value is negative because it's going backwards along that normal direction. So we put in a negative 12.856. Okay, meters per second. All right. What do we put in the numerator? Well, we actually don't know either of these values yet, all right? But what we can say is that we know once these things collide and then rebound, 2 should now have a bigger velocity than 1, and so I should probably put it first in the little difference that we have there, okay? So I'll basically say V2, maybe I'll call it V2F. It's not actually completely final, but it's V2F, meaning after this occurs, what is its new velocity? And actually, let me do this, V2 NF. Now that's a lot of subscripts, but I'm trying to indicate it's disk 2, normal direction, final, okay, minus V1 normal direction, final. Okay. Well, so, you know, one of the nice things there is that this looks like it's a linear equation, right? I can just take all these values and put them on one side. Those are 2 things that I don't know, but that's okay. All right, so this is coefficient of restitution. What's our other principle that we can use here? Okay, our other principle that we can use is that as this interaction takes place, the momentum in that normal direction is conserved. Okay, well, what do we mean by that? Okay, here's what we mean. What we mean is we add up all of our momentum that we have in the normal direction. Okay, well, what does that mean? Well, we've got 27.189 meters per second, that's the velocity, times the mass of that body, so 4 times 4 kilograms. Okay, and to this we're going to add, okay, the velocity of the other one, which is going to be minus 12.856 meters per second, times its mass, 7 kilograms. All right, and we're saying that this has to be equal to the amount of momentum that we have after the collision occurs, okay? And so we'll put those in here as well. By the way, when I wrote this V2NF and V1NF, I assumed, without saying it, but I assumed that there were going to be particular directions of each of these values. And so it's probably a good idea for me to state that a little bit more explicitly here. Okay, let me just sketch them on here with a slightly different color. I'm assuming there that both for 2 as well as for 1, we are going in that kind of positive normal direction in both of those cases. Okay, and I get the difference by taking that difference right there. Okay, that's important when I write this equation, because now we're saying that our total momentum is going to be equal to the momentum of 1, which is just going to be equal to that, you know, V1 NF that I have right there. Okay, multiplied by its mass, which is 4 kilograms, plus V2 NF times its mass, which is going to be 7 kilograms. All right, and here's what's nice. This actually constitutes a 2x2 system of equations, and it is linear. So that means that there's no reason that we can't go ahead and plug this into a solver like the one that's in the Casio. All right. So here's what that looks like. We go into the equation mode. Okay, this is the 2x2 solver. We do have to manipulate this equation a little bit over here. First thing we need to do is multiply this stuff that's in the denominator by the stuff that's on the left, and think of that as actually being on, all of it being on the right. So here's what that looks like. V2NF is positive. So let me actually start with those. So V1NF, which I'll put in first, okay, has a coefficient of -1. Okay. The next one, V2NF, has a coefficient of +1. And now we take all of this other stuff and put it in that last term of C there in the calculator. So I have 0.65 times 27.189 plus 12.856. All right, so there's that. Now we look at this other one, and we have V1NF gets multiplied by 4 kilograms. V2NF gets multiplied by 7 kilograms. And then all of that is going to get set equal to, all this other stuff is on the other side of the equation, so that goes 27.189 times 4 minus, because that's a minus sign right there, 12.856 times 7. Okay, when I hit equals, now this ends up giving me my answers for these two values. So V1NF gives me -14.858. Okay. The units on that are going to be in meters per second. Let me get the other one up here. The other one is V2NF. And it's going to be 11.171 meters per second. All right, so what does that negative sign mean? Okay, the positive sign means that the direction that we assumed here for V2NF is correct. It means the direction we assumed for V1NF, it's actually opposite of that. So it's really going kind of backwards along the kind of toward the negative n, right? That's what the negative sign means right there. It means the opposite of what we assumed. Okay? All right. This I don't believe is what we actually asked for, though, because what we actually asked for was we need the velocities of disks 1 and 2 immediately after the first impact. This gives us some of it, but probably what we're interested in is doing something either in x and y components or maybe in magnitude and direction. So let's go ahead and get this answer. We'll go ahead and express it so that we have these complete expressions of velocity of these two disks after that impact has occurred. Remember as we do this that the tangential components, when we have this frictionless impact, these tangential components, they do not, change. Before and after the impact, they remain the same. All right, so let's do this. We'll start with disk 1. So V1 X, and I'll say F as in final. Okay. All right. We have a normal component and a tangential component. All right. Let's start with the tangential component. Okay, because it does not change. So V1 tangential was 12.679 meters per second. But I don't need all of that because that doesn't point entirely in the x. I want only the component that just points in the x. And you'll see that that component of velocity right there does generally point in the x, so it should be positive, but we need to multiply it by a trig function in order to get the amount that just points in the x. And to do that, you'll notice it's the opposite piece from this 40 degrees. And so we multiply this by the sine of 40 degrees. Okay. All right, so there's that much. And then we also have the component that is the normal component. Okay, now the normal component winds up having this negative 14.858. That kind of points back this way, which is opposite of the direction of x. So we're going to say minus 14.858 meters per second. Okay, and we want only the component of that that points along the x, and to get that we multiply by the cosine of 40. Okay, so let me go ahead and punch those in real quick. All right, 12.679 times the sine of 40 minus 14.858 times the cosine of 40. Okay, this gives me negative 3.232 meters per second as my velocity along the x direction. That does mean that its velocity is to the left rather than to the right. So that's what that negative sign means right there. Okay, so that's probably worth a box because that is one of my velocity components. Okay, what about my velocity component in the y direction at the end of this impact that happens? Okay, so for that, I first see that my again, my tangential component doesn't change, and so it has this negative y component. So I have a negative, where was that tangential? 12.679 meter per second. Here I'm going to multiply by the cosine of 40 degrees, okay, because that's the component that I want. It's adjacent right there. All right, then what? So then I look at what my new velocity is in the normal direction, and since it again points kind of downward there, it will be that negative value of 14.858 meters per second, and here we're going to multiply that by the sine of 40 degrees. All right, so let's punch those in. So I have a negative 12.679 times the cosine of 40, whoops, plus, not plus, minus 14.858 times the sine of 40. All right, and that gives me a negative 19.263 meters per second. All right. What do those mean in terms of magnitude and direction? This is always an interesting thing to me. So maybe I'll just call this V1F as a magnitude of that overall. You just take the square root of the sum of the squares. So you take square root of 3.232 squared plus 19.263 squared, and that gives us 19.532 meters per second as my final velocity that I would have for disk number 1. Okay, well, what direction does that go? Okay, so maybe we'll call this theta 1f. It's going to be equal to the inverse tangent of our y component over our x component. Okay, the y component there would be minus 19.263, and the x component would be minus 3.232. Okay, when we do this, we may not get it in the correct quadrant. As a matter of fact, I strongly suspect that we will not, because they are both negative here. Those two negatives will cancel. Okay, and so it'll tell us here that we're up in quadrant 1 is officially kind of what that number gives us, 80.475. If I subtract 180, it gives me what it actually is, which is kind of 99 degrees clockwise from the x-axis. So I'll say that in here, minus 99.52 degrees, because I checked the quadrant. Okay, and that makes sense because it's going to point mostly downward, but a little bit further clockwise from being perfectly downward. All right, that is my final velocity of disk 1. What else were we supposed to do? Well, we were supposed to try to find the final velocity of disk 2 as well. Okay, why don't I slide some of this down, and I'll do that right in here. So, my final velocity of disk 2 okay, in the x direction, I have whatever my tangential component was to begin with, which was 15.321 meters per second. Okay, and I want the component of that is going to be in the x, so I need to multiply by the sine of 40 degrees. Okay, and then I'm going to add to this that component that I have after the impact in the normal direction, which is going to be 11.171 meters per second. And I'll take that times the cosine of 40 degrees. Okay, and both of those are positive in that x direction. So we'll punch those in real quick. 15.321 times the sine of 40 plus 11.171 times the cosine of 40. Okay, this gives me 18.406. And that's going to be in meters per second. My final velocity in the y is going to be similar, but notice there that my tangential component is actually going to be pointed in the negative y direction. Multiplying by the cosine of 40 degrees to figure out what that piece is that lines up with a vertical direction. Now we're going to add 11.171 meters per second times the sine of 40 degrees, because that generally points upward there. All right, so minus 15.321 times the cosine of 40 plus 11.171 times the sine of 40 gives us negative 4.556, we'll say. Okay, and those are, if we want to express it in components, That's how we would do that if we want to just figure out what the overall final velocity is. We take the square root of the sum of the squares of those values. So square root of that last value we had squared plus 18.406 squared. That gives us 18.961 meters per second. And what about the direction? So theta 2 f, again, arctangent of, we'll take the y over the x, so we have minus 4.556 over 18.406. Like that. Okay, which gives me a negative 13.903 degrees. And do I need to mess with the quadrant on that one? Let's think about it. So I do have a slightly negative component in the y with a positive x. That does put me in the fourth quadrant, okay, which that means I don't have to change this at all from just the raw value. All right, so we have now done everything that was asked in part A of this problem. All right, so we can check that off. Part A is done. The next part is very interesting because we're going to deal with the impact of disk 2 with the plate. Okay, now in order for us to really do this, as I mentioned a minute ago, we need to handle this with a conservation of angular momentum around the pin that's holding this plate. To get that, one of the parameters we're going to need is the moment of inertia for the plate around the pin. And so instead of having to bog down in the middle of the rest of my process, let me go ahead and find that I value right here and just say the I about the pin for the plate is going to be, and I'll go ahead and make this calculation. The formula for it in the book, again, I won't look this up, but I'll assert that it's going to be 1 over 12 times the mass of the plate. The mass of the plate is 11 kilograms multiplied by the length and width, each of those squared. So here I would have 1.2 meters squared plus 1.6 meters squared. Now, what this does is it finds my moment of inertia of the plate about its own centroid. Okay? It's not really what I want. I want it to be about the pin that's up here in the middle of the top face up there. So what I need to do is think about how far is it from this point up to this point. Okay? And the answer is it's going to be half of 1.6 meters. That's just going to be 0.8 meters. I use that with the parallel axis theorem. Okay, parallel axis theorem says you take the mass of that body and multiply by the distance. Okay, again, that distance there, 0.8 meters. Squared. Okay, so let me put all this in here. So I have 1/12 times 11 times, okay, here I've got 1.2 squared plus 1.6 squared plus 11 times 0.8 squared. and that gives me 10.707. This is going to be in kilogram meters squared. Okay? Now, that's interesting to us because that allows us to do calculations involving the angular momentum of the plate around the pin. Okay, let me go ahead and store that. I'll just store it into A. Okay. All right. Well, so now what? All right, that is an important factor, but now we have to actually think about the impact part of the problem. So again, let's actually do a little sketch, and the little sketch that we'll do is where disk 2 is impacting the plate. All right, and it is going to begin with a couple of components of velocity, right? So it begins with this component of velocity that comes in like this, and we found that just a moment ago, right? So for disk 2, we had an x component there of 18.406 meters per second. All right. And we're assuming that because we had so little gap between these two things, it's not going to have had any chance to move relative to the position it's shown at right there. Okay, and it's going to have that velocity at the point of contact. All right. It will also have, what else? The other component we have is negative 4.556 meters per second. Okay. The negative means it points down like this. We don't actually really care about that because that's not going to be a significant part of our problem, at least not yet. Okay. So when it does this, the initial velocity of the plate, it begins at rest. Okay, so there is 0 initial velocity. Now what we want to do is go in and sketch our directions that we're assuming these final velocities are going to be. Okay, so let's say that it approaches in like this, and then we end up with it bouncing off this direction. Okay, so maybe I'll call this V2F, V2XF. I know I already used that, but now we're talking about with respect to this collision event. This is the final velocity coming off of this collision event. Okay, and then the other one that I will identify is a velocity of the plate right here. Okay, so maybe VP, and that's going to be in the x direction. Okay, this is just the x component of it because that's, you know, we're looking along a normal line to where the contact occurs, and that's going to be as a final, you know, after this impact occurs, that's the final velocity that we have there. So here's something that I need to show. We can actually say how far this line is away from, you know, and I'll just sort of say this goes up to the pin. Okay, so maybe I'll put up here to the pin. So we're finding this perpendicular distance from this point up to the pin, and we're given over here that it's just 1.4 meters. Okay. So because of that, I can do a relationship between VPXF and whatever omega this body has around that pin. Okay, so let me do it this way. VPXF is really just going to be equal to the omega of the plate, let me just call it omega sub p after this thing has begun to move, times 1.4 meters. All right. All right, so now we have expressed the velocity of point P at the point of impact there in the x direction, final. We've done that in terms of omega and that radius value of 1.4. Okay, what we're ready to do here is actually, again, a system of equations like we did before, where we use our coefficient of restitution, okay, along with a momentum conservation equation. So first of all, coefficient of restitution, 0.65 is again the coefficient of restitution. It is going to be equal to, okay, which body had a higher velocity at the approach, right? Well, it's going to be this ball number 2, right? So we're going to say 18.406 meters per second in that direction, normal direction, minus 0, right? Because it had 0 velocity right there at the point where it contacted. Okay? In the numerator, we need the departure, right? And so now we use this omega p times 1.4 meters as the final velocity there, minus, and now I want to actually make sure we do this correctly, because you can assume whatever direction you want. V2xf, we assumed it was to the left. The thing is, if we assume it's to the left, that's actually a negative velocity according to the positive direction that we've defined here. So when I subtract, I would subtract a negative V2xf. Okay, just got to be careful with those. Now, we're going to do here a conservation of angular momentum. All right. And here's how I want to handle the conservation of angular momentum. I want to basically, the concept I want to use is that the loss of angular momentum that happens with the disk that comes in and hits here is the amount of gain of angular momentum of the other part, the little rectangle that's hanging down there, or I guess we're actually viewing it from above. So it's not hanging down, but it's that rectangle is going to pick up angular speed, which it picks up angular momentum when it does that. Anyway, the loss of angular momentum that happens of the disk that hits it is the gain of angular momentum of that rectangle. Okay, well, here's what that looks like. Okay, it starts out with a angular momentum based on this 18.406 meters per second. Okay, and we're really just going to look at the, there is no change in angular momentum that happens due to the tangential component here, because it just remains at that same speed with the same mass and everything going that direction, so we don't have to worry about that. We're just going to look at the change in angular momentum due to the fact that this disk hit this other thing. Okay, so final minus initial, all right? So final is going to be equal to minus V2xf times the mass of that body, and the mass, I believe, was what, 7? Yeah, disk 2 has a mass of 7 kilograms. Now here's where this gets just a little bit tricky. In order to figure out what the momentum is, or the angular momentum, we also need to multiply this by how far we are away from the point that we're evaluating momentum around, which is that pin. So we need to multiply this by 1.4 meters. Okay. All right, and then we're going to subtract from this because we're trying to find final minus initial would give us the change, right? So, you know, the change in angular momentum that I have here, let's see here. That's right. The change is going to be final minus initial. So the change in angular momentum that I have here involves V2 initial, which is going to be 18.406 meters per second. All right, times 7 kilograms times 1.4 meters. Okay, so where it had a certain amount of angular momentum to begin with, then it ends with a different amount of angular momentum. All right, what does this equal? This equals to the moment of inertia about the pin, 10.707 kilogram meters squared. All right, multiplied by that angular velocity that I have at the end, omega p times, or it doesn't need times the 1.4, just omega p. All right, so again, just to recap, the amount of angular momentum change that I have in, you know, caused by the disk that comes in here is going to be equal to the amount of angular momentum picked up by the plate that's hanging there, or that's set there on the pin. All right. So what do we do with this? Well, notice here that I have a system of equations where one of the things I don't know is omega p, and one of the things I don't know is V2xf. Let's go ahead and punch those into the calculator. All right. We're going to do a 2 by 2. Okay. I guess I'll go ahead and use omega p as my first one to enter here. So I'll say that's going to be multiplied by 1.4. The next one that I have is my V2xf. It's a double negation there, so I'll just have positive 1. Okay, and then over here, I'll have 0.65 times 18.406. All right, now down here, okay, I will put in, I'll pretend like this is the side of the equation I'm working with over here. So I'll just put in, I believe I had that value stored in A. Okay. Now I need to take this other one and move it to that side of the expression. So that would be positive 7 times 1.4. Okay. And then I leave this one negative because it's still on the opposite side from where I assumed those were. So I say negative 18.406 times 7 times 1.4. All right. And that gives me a final angular velocity of 98.769. And it gives me a VXF, V2XF, of negative 126.31. Okay, meter per second. Now, I didn't necessarily do this on purpose, but I am actually a little bit concerned when I look at this this setup right here. Why am I concerned? Okay, it makes me think I made a mistake earlier in my process. Okay, the reason I'm concerned is that it looks to me like we picked up energy somewhere. All right, if omega p is this large and V2XF is this large, then it looks to me like we have some sort of an issue with picking up energy somehow. Okay, so I need to go through and actually very carefully check all of my assumptions here. Okay, so I think it looks to me like probably what went wrong is that my amount of momentum loss that I have here, I may have done this wrong. Okay, so again, I did final minus initial. Is that appropriate? Because what that does is it tells me the amount of change. So if that is negative, then it's going to give me a negative change over here. So again, I'm troubleshooting my own solution in real time here, so I'm hoping that that's correct. But now that I'm looking at this more carefully, I think that that's what I did wrong, is that, you know, I have a change here. That change should actually kind of be equal to the negative that I had over here. So if I take all of this and count it as negative, I think that fixes it. All right, so let's actually try punching that in and see if that does in fact fix it. Okay, so down here I would again put in just A, but here I would put in the negative of this. So the negative 7 times 1.4. And here I would again negate that, and so it would be positive 18.406 times 7 times 1.4. And now I hit equals. I like this a lot better. Okay, this makes much more sense. So it tells me here that this omega that I would have would be 12.184. radians per second, and this is going to be equal to negative 5.094. meters per second. All right, now, you know, I do these videos a lot of times. If I make some minor errors or something, I edit it out, you never see it. I think I'm going to leave this one in here because this is a really good example of, you know, making an honest mistake as you go along, thinking about this change in momentum wrong, and because of that, ending up with an answer that didn't make sense. How do you go back through and then try to find that? Well, you know, I basically, as I did this, I'll just be honest, I took a stab at this, and then I realized later that that was probably the wrong change, the wrong direction of change that I needed for that change in momentum. I'll leave this in here as an example. It says, check your work along the way, see if it makes sense. I'll say this makes a lot more sense relative to the numbers that I was seeing earlier in the problem. All right, so now what do we think about this? Well, the negative that we have here actually means that this direction that I assumed for this velocity is wrong, okay? It means that after this impact happens, that disk continues to the right. It doesn't bounce to the left, it actually continues to the right. That's what that negative sign that happens right here means. Continues to the right. This one came out positive, which we would expect that omega is going to be counterclockwise, just like we assumed it would be. All right, so what have we actually accomplished here? Well, I think this 12.184 radians per second allows us to answer part B. All right, now part C, find the final velocity of disk 2 after the second impact. We're halfway there in finding that. Actually, we're most of the way there because we already knew what the initial y direction velocity was, 4.556 meters per second. Okay, so v2yf is still negative 4.556 meters per second. Okay, so if you want it in components, that's how it's given. If you want to do it as a magnitude, okay, v2f, you just take the square root of the sum of the squares of those. All right, so here we're going to take a square root of negative 5.094 squared. Oops, better not leave that negative in there because it's not going to handle that correctly if I don't have parentheses as well, plus 4.556 squared. Okay, so that gives me 6.834. meters per second. All right, as my magnitude as far as a direction. Okay, we'd look at the y, which is negative 4.556 meters per second. Okay, be careful here, right? Because if we're trying to do this relative to the positive x direction, and I assumed this was in the negative already, I want to put a positive 5.094 down here. Okay, kind of be careful with that. I know that it gets confusing if you have these double negations, but I assumed left. I was wrong is what the negative sign means. It's actually going to the right. In terms of doing the arctangent function, you always want to make right positive and left negative. So 5.094 indicates a movement to the right in the x. All right, so we'll punch those in. Arctangent of negative 4.556 divided by 5.094, which gives me negative 41.81 degrees. Okay, now do I need to check the quadrant? Well, negative in the y and positive in the x does put you in the fourth quadrant. And the fourth quadrant is also where the negative 41.81 implies. So it looks like we are good there. All right, so that is the magnitude of direction of the final velocity of disk 2. We already had the magnitude and direction of the final velocity of disk 1 from the last time. And so I believe that we have now covered all of the requested items in this problem. I hope this has been a helpful video with respect to learning about impact, and if it has, I would appreciate it if you would subscribe to my channel. I'd also appreciate any likes that you might put on there, and comment for sure if there are any questions or confusion about this problem. Thank you for watching.